to GeoHug. So I'm just promoting you up as panelists. Please don't be shy. Come on through. You can get your cameras on, get your mics on. We have the lovely Louise Schoneveld with us today. But before we do get stuck into today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I'm thrilled that we have Louise Schoneveld with us today. So Louise is a senior research scientist with the Mineral Resources Division at the CSIRO, and she's currently investigating the changes in trace element signatures as possible indicators for magmatic nickel, copper, cobalt, platinum group element mineralization. And I'm, just very, very excited that she's here to share this with us. So yes, thank you so much, Louise, for joining. I'm really grateful to have you here.
Yeah, no worries. Glad to be here.
Before we do get stuck into your presentation, I was curious what got you into geology in the first place.
So I was always into science and all things science, but during high school, I actually had an earth science course in year 11 and 12, taught by a very enthusiastic female earth science teacher. And it was just really fun. And I had a good time studying it and learning all about the earth and earth systems. And then had to choose what I was going to do in university and thought I would keep having fun in geology. And I've just continued to do so ever since.
I love that. And so what's been some real career highlights for you so far?
Definitely traveling to conferences and seeing different parts of the world and talking about science is what I really enjoy doing.
Yeah.
So that's definitely been the highlight so far.
I love that. What would be like your favorite geological place that you've been to so far?
When I first started at CSIRO, my supervisor and I went to Hawaii to learn about volcanic flows and relate them to komatiitic systems and nickel sulfide systems. And that was really cool to see just volcanic flows in Hawaii.
I love that. That's amazing. And you've got a pet rock here for us today. I would love
Sure
to
do.
know about that.
So this is my favorite little rock. It's a geode that I got from a museum in the Atherton Tablelands in Cairns in Queensland. And it was just, you got to pick the big ball out of a box and then use a chain to crack it open, and you get to be the first person to see what's inside. And this one was a little amethyst geode.
I love that.
And it was just great to be the first set of human eyes to see whatever was inside this little geode.
That is super special. Thanks for showing us that. That's super cool.
Nice.
Well, yeah, thank you. Thank you for joining. It's awesome having you here. If you want to share your screen, and yeah, we'll get stuck into it.
Sure.
Perfect. Thank you.
Alrighty, so I'm here today to talk about our research that we just wrapped up for indicator minerals for nickel sulfide exploration. So as many of you probably know, nickel is extremely important in our progress towards green technologies and especially in rechargeable batteries. Lots of people are looking at buying electric vehicles, and each electric vehicle battery has 29 kilograms of nickel in it. So we need to find more nickel deposits to be able to meet this increasing demand for all the rechargeable batteries we're going to make in the future. There's two types of nickel deposits. There's nickel laterites, which are formed through the weathering of ultramafic rocks, and then nickel sulfide. So nickel sulfide are more high grade deposits and usually a lot cleaner metal. And Western Australia has both nickel laterites and nickel sulfides, and Australia is currently producing 8% of the world's nickel, but there are a lot of nickel deposits in Western Australia that are currently not being not in production, but have the potential to produce nickel as well. So Western Australia is an excellent place to explore for new nickel deposits. However, we think that we've found most of the nickel deposits that are at the surface. So we need to start exploring under the cover to find any new resources. So we think that indicator minerals will be able to help for exploring undercover. Indicator minerals have been used in the diamond exploration industry for many, many years. The high pressure environments that form diamond also form a bunch of different minerals like garnets and pyroxenes. And the colors of those minerals, like the deep red of the garnet and the bright green of the pyroxene and the yellow olivine, signify that they form at those high pressures. And you might be in a region that contains diamonds. So you can just look at the color of those individual minerals to see whether or not you're in a prospective place for diamond. For magmatic sulfide deposits, they can occur at any pressure. So we don't have the luxury of using pressure as our indicator. So we're looking at one of the other processes that are involved in magmatic sulfide deposit formation. So to form a magmatic sulfide deposit, you usually need a flowing silicate magma that incorporates sulfur in it somehow, let's say by the melting of sulfidic sediments until you reach the point of sulfide saturation. And then you have little sulfide droplets that interact with the silicate magma and eventually get accumulated. So we're looking for evidence in the chemistry of our minerals that reflect any of these three processes. Indicator minerals can be resistate in nature, which means that they survive at the surface, and these can be used to vector toward mineralization. Here on the screen is a diagram of kimberlite, a buried kimberlite. And as you move closer toward the source, the abundance of your mineral phases becomes higher, and also the size of your mineral grains becomes higher as well. So you can vector towards your source. So we hope to do the same thing with magmatic sulfide deposits. We're looking undercover as well, which means that we have the potential for the formation of supergene and diagenetic indicator minerals as well, but we're not going to cover them in this talk. We're going to focus mostly on the detrital indicator minerals, which are the physical weathering of the rocks of interest, or the residual indicator minerals, which have been moved away from their source. We're also looking at in situ indicator minerals. So these are minerals that are found by drilling into the host rock, and they can give us clues as to whether or not the rock is prospective for nickel sulfide as well. So when we started this project, we wanted to use indicator minerals in a new way. We're not looking at just the presence and absence of minerals alone, but we're also looking at the trace element concentrations within each of the minerals to understand the formation histories and whether or not sulfide may have been present and interacted with those minerals. So luckily we were able to gather funding for this very large project. It had a lot of industry sponsors, which are all shown on the right-hand side of the screen, as well as MARIWA, which is the Mineral Research Institute of Western Australia, who also contributed to the funding for this project. We had 12 detailed case studies that include komatiitic nickel deposits, intrusion-hosted nickel deposits, lateritic nickel, barren rocks, greenfield exploration, and also globally recognized nickel deposits as well. So all these little blue boxes you can see are the locations of our samples throughout Western Australia, and we totaled 1,150 samples for the project. So we have a lot of indicator minerals that could potentially be used for nickel sulfide exploration. They're all listed on the screen here. I don't have time to go into detail into all of them, but I will cover the three major ones that we found throughout this project. So unlike in diamond systems, we can't visually see a color change that represents the change in chemistry for these minerals. So we have to rely on tools and technology to be able to understand the changes in chemistry of each of the minerals. So we relied on TEMA, which is an automated mineralogy technology that's hooked up to an SEM. We calibrated the libraries so that they are correct and robust, checking them against thin section images as well to ensure the mineralogy is correct. And using this technology, we can not only make mineral maps, as you can see on the screen here, but we can also extract the mineral chemistry. So each of the each grain inside these mineral images can be extracted to understand their variations in chemistry. In doing this, we focused mainly on Spinels, and we ended up with about 50,000 Spinel major element analysis from the basement rocks, and then an extra 26,000 from surface and regolith samples as well. So you can gather a lot of data using this technology. You can also use this technology to be able to visualize the changes in chemistry, like you can just optically in as you can with the diamond indicator minerals. So here we've put chromite in red, magnetite in blue, and chromium magnetite in purple. And you can see that now we can visualize the abundance of each of those Spinel mineral phases and their sizes as well. The SEM and TEMA technologies are also really good at being able to hunt for rare grains. So this is a grain mount of thousands and thousands of grains, and we were able to locate a single sulfide grain at the surface. So this is a soil sample. So using this technology, we're able to process and understand the chemistry in thousands of grains at once. So as well as the major element chemistry, we looked at the trace element chemistry in each of the minerals using the laser ablation inductively coupled plasma mass spectrometer, or LAICPMS. So this technology drills a small hole in each of the minerals and gives you concentrations of elements in those minerals down to parts per million level. It's pretty quick. It only takes a minute per analysis, and you can get really, really low levels, accurate, precise, and low detection limits of each of your elements. So we relied heavily on the major element data gathered by TEMA, ending up with over 100,000 major element analysis, and also the laser ablation ICP-MS for the trace elements, and we ended up with 20,000, well, 18,800 trace element analysis of mineral phases. You can see that we focus mainly on Spinel, but we have covered olivine, pyroxene, ilmenite, plagioclase, apatite, zircon, sulfide, serpentine, and amphibole as well. So there was a lot measured in this study. We focused mainly on the intrusion-hosted nickel sulfide deposits, but we have covered komatiitic nickel as well as vanadium titanium layered intrusions. And we have a pretty good split in our samples between mineralized and unmineralized samples. So because we've collected a very large, robust and consistent data set, we were able to put all of this data into machine learning models. Using these models, we broke the data into a training set and a testing set, making sure that anything that was in the training set wasn't also in the testing set. So this makes sure that the models can't find shortcuts between a sample that may be in both the training and testing sets. And we put it through a bunch of random forest machine learning models. So what we wanted to get out of these machine learning models was how well these models predict whether or not the sample was mineralized, what elements are used to make that prediction, and whether or not these elements make geologic sense. So the way that we interpret the machine learning models is we have the predicted label at the bottom and the true label on the y-axis. If the model was completely 100% correct, these two boxes would have ones in them. So this deviation is the percentage of false negatives and false positives that you can expect from these machine learning models. So it just gives us an idea of how confident we can be in the predictions that the machine learning model is putting forth. Because not everyone is comfortable in using machine learning, we made decision trees from the machine learning models where as a user, you would analyze a mineral. It would have a certain concentration of magnesium. And if it's greater than a certain amount, you would follow the decision tree down until you come up with a decision. So this sample would be unmineralized, but you can see that the confidence is only about 70% confident, whereas this one, the label would be mineralized, but it's a lot more of a confident decision. So these decision trees will be published in the final report that is going to be made available in 2025, but all of the values are currently confidential, so they're missing from this chart. But they will be available in 2025. So Spinel was our main focus in this indicator mineral study. It occurred as both fresh aluminium chromite grains, as well as altered chrome magnetite phases. And the Spinel group also includes magnetite, which can crystallize directly from sulfide. So this is a big chalcopyrite sample with magnetite that's crystallized directly from the sulfide liquid, or the magnetite can also crystallize from the silicate liquid. So this is a sample of pyroxene and amphibole and magnetite rock. So doing the hundreds of thousands of major element analysis of Spinel, we found that the major element in Spinel are pretty good at fingerprinting their host rock. So this was also put forward by Barnes and Roeder in 2001, and we've just confirmed that the major element compositions that they outlined for basalt and komatiites and various other host rock types are pretty accurate to what we measured as well. So the major element chemistry of Spinel is pretty good at fingerprinting its host rock. Moving on to the trace elements, the machine learning models had a pretty good go at predicting whether or not the sample was mineralized or unmineralized. You can see it's pretty accurate at making that distinction using the trace elements analysis. And we found that titanium, vanadium, manganese, and nickel were the most important elements in making those decisions. So this means that Spinel will be pretty good as both ex situ and in situ indicator mineral when measured trace elements are put through these machine learning models. Another interesting aside is that we were able to predict the volume of sulfide that was associated with the Spinel as well. So this suggests that if we refine this model a bit further, we may be able to analyze the trace elements in a Spinel and be able to say whether or not it's prospective for sulfide, but also whether or not the deposit may be big or small. So that needs a little bit more development, but it is a promising result. Another little extra bonus for Spinel as an indicator mineral is that it has the ability to carry micro inclusions of various phases, such as platinum group mineral phases, and also secondary sulfide mineral phases. So if you have access to an SEM, you can look at these inclusion populations, and it may also indicate that these Spinel crystals have been in contact with a melt that has reached the point of sulfide saturation because it has some little sulfide inclusions in it. One thing you do have to be careful of in chromite is many of the chromite, especially in komatiitic systems, have a tendency to be zoned due to metamorphism, which does change the ratio of the major elements throughout the crystal structure. So these zoning should definitely be observed if you start using trace elements in chromite as an indicator. We also looked at ilmenite as an indicator mineral. It also has a pretty accurate prediction of whether or not the system is mineralized or unmineralized. And just from looking at it on bivariate plots, it seemed that magnesium ilmenites are a pretty good indication of nickel-bearing systems, where the machine learning models rely mostly on the trace elements of chromium and niobium to make the prediction of whether or not it is mineralized or unmineralized. So ilmenite would make a really, really good ex situ indicator mineral because it's found very commonly at surface in soils and sediment samples. We looked to the heavy mineral map of Australia, which was published late last year, which contains heavy minerals separated from stream sediments across all of Australia. This data was measured via TEMA. So we have a very large TEMA library with elemental concentrations taken off the TEMA, and we were able to use the machine learning models based off of that data to make prospectivity predictions of the heavy minerals collected in the heavy mineral map of Australia. So far we've only done Western Australia because all of Australia has a little too many grains for this study. So because we only got the data in late last year and this indicator mineral project also finished late last year, I had a period of about a month to try and come up with prospectivity maps for Western Australia. So we focused mainly on magnesium ilmenite because it is very, very common in the heavy mineral concentrates. We found, so this is a map of the magnesium ilmenites overlaid over nickel deposits. So all of these little blue squares are known nickel deposits in Western Australia. And if the circle is very, very big, then it has a high proportion of magnesium ilmenites and also a high number of magnesium ilmenites. So you can see that this section of Western Australia has a lot of both high proportion of magnesium ilmenite and a high number of magnesium ilmenite, suggesting that it's a prospective region. And it does correlate with this known nickel belt in Western Australia. However, the main nickel belt of sort of Kalgoorlie region is missing in this analysis. So we still have to go through looking at where each of the streams was sampled and where it's draining from, and understand these prospectivity maps in more detail. But it does look like it is able to find some prospective regions for nickel at surface. So moving on to pyroxene. Pyroxene is a heavy mineral, but it's unlikely to survive in the weathering profile or regolith profile. So it's more likely to be useful as an in situ indicator mineral if you drilled into an intrusion that you thought may or may not contain nickel. So back in 2020, we published a study stating that intragrain zonation of chromium inside pyroxene is commonly observed in nickel sulfide deposits throughout the world. There's a QR code on the screen that I'll give you a couple of seconds to zap if you wish to access that paper. It is open access, so you should have access to it no matter what. So we found pyroxene grains like this that have a very complicated zoning pattern of their chemistry throughout the crystal structure. We observed these zoning patterns using XRF mapping technologies. There are a bunch available. Each of them vary in their spot size and resolution, but most of them can see that zoning pattern. You can even see it sometimes in thin section. So the Australian synchrotron is the best resolution. You can get down to 1 micron spot size, but the access to the Australian synchrotron is based on merit-based proposals. So getting access to it for an exploration program is probably not feasible in time or money. The Maya mapper, which I don't have an example of here, but it's a bit smaller. It's a lab-based technology, which has a 30 micron spot size and is used to measure drill core sized samples. And then we have little desktop model XRF mappers, which can measure some core samples, but are usually used to measure thin section size samples. The synchrotron is very, very good resolution, but it's using the Maya detector, which means that you can't detect anything lighter than silicon, which means that we can't quantify magnesium and other elements that we've been using for differentiation in the Spinel system and the pyroxene system. Similarly, the Maya mapper, which is our lab-based system here at CSIRO, is also using the Maya detector system, which has the same issues. It can't measure sodium or magnesium, so we can't get quantitative element chemistry, but it does make good maps at quite a large scale. And then we have the desktop XRF units, which the most common ones are the iXRF Atlas or the Brooker Tornado M4+. And these are just little desktop units that have the ability to measure light elements as well. So you can do quantification of sodium and magnesium to be able to pull out the major element chemistry of each of these mineral phases. So we did try and use the XRF mapper to quantify Spinel grains as well, because the sample preparation is a little bit less involved than it is at the TEMA. With the TEMA, you need to cut it, polish it, and coat it in carbon before you analyze it with the TEMA. For the desktop XRF, all you need is a cut flat surface. So it saves a lot of time in sample preparation, so we were interested to see whether or not it was any good at actually quantifying the major elements in the Spinel. And it's okay when the Spinel grains are greater than about 100 microns in width, but when you get to very, very small grains, the scatter in the data is very large. So although we can use it for quantification, it's only suitable for larger grains. But no matter which XRF mapper you use, they're all good at giving these visualizations of the change in chemistry in a grain. So throughout many of the famous nickel sulfide intrusions throughout the world, we did find these complicated zoning patterns in the pyroxenes. In both orthopyroxenes, which are showing up in like oranges and reds, and the clinopyroxenes, which are showing up in pinks and purples. And this zonation pattern is mainly focused on the changes in concentration of chromium, but can also be seen in titanium and other trace phases. When we looked at pyroxenes in similar intrusions of similar size, age, and region, we didn't see this zoning pattern at all. The most zoning we see is this normal zoning, which is a diffuse change from high concentrations in the core to low concentrations at the rim, which is just a normal crystallization process. So these zoning patterns record a little bit of the crystallization history of that crystal as it was forming. As I said, normal zoning is just the normal change in the magma chemistry as the crystal grows, where the compatible elements are high in the magma and therefore in the crystal at the start of crystallization. And then as the crystal begins to grow and the whole magma chamber becomes more solid, the compatible elements are used up and therefore become lower concentrations towards the edges. These other zonation types are a little bit more complicated. This sector zoning is thought to occur due to rapid crystallization of the pyroxene. This abrupt zoning is usually due to a rapid change in chemistry or an influx of new magma into the system. Oscillatory zoning are a good indication of rapid changes in either the chemistry or new magma pulses coming into the chamber. And then complex zoning is any combination of B, C, or D, so these three. So in this one crystal, we can see sector zoning, abrupt zoning, and oscillatory zoning. So we know that our clinopyroxene grew pretty fast. At one point, there was an abrupt change in the magma chemistry. And then throughout the end of the growth of the clinopyroxene, there were lots of small changes in the chemistry. So this clinopyroxene grew during a very, very active system, which is a pretty good indication that we're probably in a dynamic magma chamber where there is a lot of new magma injecting in, also wall rocks melting and being incorporated into this chamber, which changes the chemistry that that little pyroxene was growing in. These environments are also really good for magmatic sulfide, because if sulfide was present in this system, it would have the opportunity to interact with a lot of silicate magma, which would increase the metal tenor of those sulfides. So although these zoned pyroxenes aren't a direct indicator of sulfide saturation, they are an indication that you might have metal-rich sulfide if there were sulfide present. So that was published in 2020. There's that QR code again if you missed it before. But at the end of this study, there was 2 questions remaining, which was how far the zoning extends away from the visible sulfide, because in the study that we first published, we were looking at the pyroxenes that were directly in the ore zone and pyroxenes that were from barren intrusions. So we wanted to know if that zoning extends within the same intrusion some distance away from the actual sulfide. And then we also wanted to know if the zoning could survive transformation to amphibole, which is a very common hydrothermal alteration of these older rocks. So to answer the question of how far the zoning extends away from the sulfide, we looked at Nova Bollinger, which is an ore deposit in Western Australia. We looked at 2 drill holes through the Nova ore body and looked at the pyroxene bearing units and whether or not there is chromium zoning throughout each of those pyroxene grains and samples. So the thought of how Nova formed is an injection of sulfide bearing magmatic mafic magma, ultramafic magma, that bifurcates in the sill so that we have the lower intrusion, which has all of the heavy sulfides in it, and then an upper intrusion that slowly inflates to create the barren upper intrusion. But if you were to drill to the bottom of this upper intrusion and go into country rock, you may miss the actual ore body, which was bifurcated below that seemingly bottom edge of the upper intrusion. So we were interested to know whether or not the zoning extends into the upper intrusion to give us a clue that there was sulfide around. What we found is that within the lower intrusion, we did find abruptly zoned orthopyroxene and clinopyroxene up to about 85 meters away from the disseminated sulfide and about 150 meters away from the massive sulfide. But we didn't see those zonation patterns in the upper intrusion. So these are our upper intrusion pyroxenes, and you can see there's no zoning at all in the orthopyroxene and clinopyroxene. So it does look like the zoning within the same intrusion as the sulfide does contain complexly zoned pyroxene, but it doesn't extend into the upper intrusion. So to answer the question of whether or not this zoning survives the transformation to amphibole, we turn to Kavitsa, which is located in Finland. It's now an open pit mine that's producing nickel sulfide. And we analyzed a bunch of different samples from the different ore zones. There are 3 different ore types in Kavitsa. One that is very nickel rich, and one that contains no nickel at all, and then the other one that just contains sort of moderate amounts of nickel. So using the synchrotron XFM beamline, we were able to collect this beautiful X-ray image, which has chromium in red, manganese is green, and titanium in blue. And you can see these orthopyroxene grains are all sector zoned, and these clinopyroxene grains in here, which are all the reds and purples, are extremely complexly zoned. And then we have some transformation into amphibole due to hydrothermal alteration. So a lot of all of the clinopyroxenes basically are complexly zoned in their chromium content. And once you start to transform them into amphibole, it begins as this patchy alteration, which does mimic the chromium content of the pyroxene. So you can see we have high chromium patches of amphibole here and low chromium patches of amphibole in the center of this grain. So we termed this ghost zoning because you can still see the underlying zonation of the pyroxene beneath this amphibole alteration. But as the hydrothermal alteration progresses, unfortunately, you do lose all relic zonation in those grains. So here you can see there's complicated zoning in the pyroxenes. You can still see it a little bit here. It starts to be ghost zoning down here, and then we lose it completely in the clinopyroxene. It does seem that orthopyroxene survives a little bit more robustly than clinopyroxene does. So in these hydrothermally altered intrusions, it might be better to look toward the orthopyroxene than the clinopyroxene as an indicator. So the complexly zoned pyroxene could be used in situ if you drill into an intrusion. Seeing these zoned pyroxenes may give you an indication you're in an active system and therefore could have metal-rich sulfide. We also did find some of these grains of abruptly zoned pyroxene in till above the Kavitsa deposit. So if you're in a region that has glaciated terrains with very little chemical weathering, it's also possible that these zonations in pyroxene could be used as an ex situ indicator. So I've only gone through 3 of the minerals that have potential as indicators. This is a bit of a summary of the other minerals that I mentioned and what we think they are most likely to indicate in the system. Poor little plagioclase doesn't have a purpose for an indicator mineral as of yet. but I will keep working on it and hopefully find something that Plagioclase is useful for. But the rest are showing promise for sulfide saturation indicators, host rock indicators, and even sulfide accumulation indicators. So indicator minerals can be used at all scales. I showed you the heavy mineral map of Australia, which is surface sampling at a regional scale and can give us prospectivity analysis at a very large scale. Moving down to tenement scale exploration, you can sample in the cover as using drill core or soil sampling. If you do heavy mineral concentrates of minerals such as spinel, ilmenite, apatite, or sulfide, obviously, it can give you a clue as to which parts of your tenement are more prospective. And then, of course, at intrusion scale, you can use almost any mineral that we've talked about, which can give you an indication of whether or not the intrusion that you've hit is prospective for sulfide without having to drill it extensively. So our indicator mineral workflow takes the form of a mineral chemistry database and a massive report, which will be available in February of 2025. It outlines what to sample for indicator minerals, where to sample, how much to sample, which of the analytical techniques are best to use, and how confident you can be in the prospectivity analysis that is given to you at the end. So this was a very large project worked on by a number of different people here at CSIRO. So if you want any more information, please feel free to contact me or visit our website, or if any of these people are familiar to you, feel free to reach out to them, and I'm sure they can answer any questions you have as well. Thank you.
Thank you so much. That was really cool to see what you've been doing. So thank you for sharing that with us.